This all begins with my cousin who got bored one day and he took his guitar and his phone and he dropped his phone and the guitar and shot a video, and you could see the strings move from inside the guitar, and it was really fascinating. And it got me wondering though, why do they look that way? And then it got me wondering, well, why is a guitar put together like it is? Like the frets, for example, towards the nut, the gap's pretty wide, but as you go down towards the bridge, the gap gets smaller and smaller and smaller. And what's the relationship between that and the notes that you play? This is a story of how a guitar is put together to be a musical instrument. Without chasing the rabbit too far, we do need to get into a little bit of math, physics, and music theory in order for this whole story to come together at the end for you. We'll make it quick. Guitar's string vibrates, making a wave from one end at the bridge to the other end at the nut. The string's wave disturbs the air, making a wave in the air, which is a sound wave, and that's what it is we hear. We actually hear the shape that the string makes. It's pretty cool. Now, how far above or below the neutral position of the string is how loud it will be. What makes the pitch, though, is how fast the wave is, how many times it makes a complete cycle, so how many times it starts over in a given amount of time. That's what we call the pitch. Now, here you can see that the cycle's beginning at the beginning of the fretboard, and it ends at the pickup hole right there. What we're going to see here is two different shots of the same string, the same note, one being struck harder than the other. And what you can see in slow motion is that the pitch is the same, but the amplitude is greater. And in the second one, the amplitude is much greater. It means the string's going farther up and down, but one wave covers the same amount of distance from the beginning to the end of it, and it's much louder. The lowest note on a normally tuned guitar is an E, and it has a frequency of 82.41 hertz. Now the next E, an octave higher, is double that frequency, so it completes a cycle, 164.82 times per second. Now what I'm going to show you is how we come up with all the notes in between. It's a little mathy, but stick with me here because it's not real complicated. Okay, so here's what we do. We take our first note, whatever its value is, and you multiply it by 2 to the 1/12th power. And that'll give us the frequency for the next note, which is an F. And that turns out to be 87.31 hertz. Okay. Now the reason we multiplied by 2 is because the next octave is double the frequency, and the 1/12th power is because this is our first of 12 steps in between the E and the octave of E. Okay. Now for the next note, we would take our 82.41 hertz and multiply by 2 to the 2/12ths power because it's the second step. And the last one we're going to do, just for this example, just strike home the point of why the multiplying by 2 and the exponent is to the something of the 12th power. So what we do to find the G note is we take our frequency of 82.41 and we multiply by 2 to the 3/12ths power. Now again, the 2 is because the octave has a double frequency, and we want a 12 notes spaced in between, nice and pretty. So we do the third note's going to be the third 12ths power. So if you don't understand how the exponents works, it doesn't matter, but that's where it comes from. That's how we come up with the different notes. Now, a good question is, if all the strings are the same length, then why do they have different notes on them? And that's a rabbit we're not going to chase, other than to tell you that it has to do with the string tension. Okay, we're almost there. What I'm going to show you now is how the fretboard is constructed. An internet search will show you that you take your scale length, which is the distance from the nut to the bridge, and divide that by 17.817. So for a guitar like mine, it's got a scale length of 25.5. You'll see that the first fret will be 1.43 inches from the nut. Alright, now we repeat the same process. The remaining string length is 25.5 minus the 1.43, and you divide that by 17.817, you get 1.35. That's all fine and dandy, and but I'm a little curious where that 17.813 comes from. Turns out that when I do the math, I think the ratio should be 17.83. But we'll get into that in a little bit later. In the meantime, I went ahead and calculated all the fret distances, and here they are. Now here's the payoff. If you take any two consecutive frets and you take the ratio, you get 1.059 or 1.06, depending on how accurate the measurements were. Alright, big deal. It is a big deal because 2 to the 1/12th power is 1.059. So what we're saying is that all the notes that you see on the left of this column have the same relationship, if you take the ratios, as all of fret spaces on the right. And that's really cool because that means the guitar shows you the relationships between the notes you hear. They don't seem to match up, but that's just perceiving the same information with different senses. So what we're seeing is, we're seeing that the notes are created from waves that are created when we move the string, and then when we hit a fret that's lower down the fretboard, it shortens the string, which makes the frequency or the note, increase. And what we're seeing is that the guitar's fretboard is laid out in exactly the same pattern as consecutive notes. We can see the relationship between consecutive notes when we look at the spaces between the frets on a fretboard. That's really, really cool. That's not something you see on a piano or definitely not a saxophone or another instrument like that. The guitar, wicked cool.